Welcome everyone. My name is Ricardo Lima, and today I'm going to present our paper entitled Automatic Design of Deep Neural Networks Applied to Image Segmentation Problems. This work was developed in conjunction with Aurora Pozo from Federal University of Paraná and Alexander Mendiburu and Roberto Santana from the University of Basque Country, Spain. So during this presentation, I'm going to talk about a little bit of image segmentation and cover the UNet. Then I'll be presenting a little bit about the dynamic structured grammatical evolution. That is the approach we apply to solving our problem. More details on our approach on the automatic design of UNets, some of the experiments, conclusion, and future work. So in the introduction, image segmentation is basically a problem where you want to assign a label to each pixel of an image individually, so you can analyze images and transform them in such a way you can identify objects, people, different objects combined like clothes in a person, and the applications where you often see such techniques being used are medical applications and security, self-driving vehicles, where you have to keep analyzing in an image or a video and keep taking decisions based on the information you collect. So one of the, I guess, most common approaches you can use to solve to segmentate images or solve segmentation problems is by using the UNet. And the name UNet, it's because the architecture of this network contains this U-shaped structure. And basically, the UNet is a feed-forward network divided in three main parts. As we can identify as the left part, that is responsible for learning features and decreasing the dimensions of the images that will contain the weights that will learn these features. And then the right part, where you have the reconstructing part that will generate the segmentation of the image that has been passed as input. And you have also these, what we call bridge connections, that also carry information from previous layers to the layers on the right part of the network, and it will help reconstructing, adding the information you already have during the training of the network and information from the previous layers without that learning. So on the motivation for this work, we know that deep neural networks offers too much customization that is often left unexplored. Designing architectures usually require expert knowledge about the problem. Combining the right modules and layers and types of parameters have a great impact on the network's performance. And having to automatically design architectures has the potential to greatly reduce the cost involved in designing those networks. So as the main objective for this work, we have that is proposing an efficient approach to automatically design deep neural networks, reducing the need of an expert on the problem being solved. And to do that, we explore the UNet architecture used for segmentation tasks. We propose a grammar that allows the creation of variations of the UNet. We employ the use of grammatical evolution to design these networks, and we compare the best design architecture with the original design. So now on the dynamic structured grammatical evolution. As similarly to the traditional grammatical evolution, we have a grammar that is basically composed of what we call the rules. And each rule has its own a list of possible productions. And each production can have different options that is usually divided by this pipe symbol that indicates when you are applying the start rule. For example, you can choose either expression, operator expression, or just an expression when you're performing the mapping or the grammar expansion. This new improved version of Grammatical Evolution has a new encoding strategy that helps reducing the high redundancy and spatial problem the original technique has. And the main difference here is that rather than having a list of integers, the DSGE encoding is a list of lists containing the integers that are directly related to one of the non-terminals of the grammar. So if you take a look on the possible rules that we have for this example grammar, we have the start expression operator in term. And here, one possible solution would be if we're consuming values to choose a production for the start rule, we would pick values from this directly from this list, for the expression for this from this list, and so on. So when performing a mapping operation to transform a genotype into the phenotype, that is in our case the neural network, all the values are being used, and we don't have the situation where two different solutions can map to the same network. On the mapping procedure, it is very similar to the original mapping from Grammatical Evolution, but as I said earlier, here all the values are used at the end of the mapping, and the values are picked directly from the list that is related to one specific rule. So here, as an example, the start rule will consume the value from this first list, and in the second iteration there's no more values because this is the start rule. Then we will be replacing each non-terminal for a new option, be it another non-terminal or terminal values. And at each iteration of the process, you'll be consuming values from the respective list until we have all terminal values and all the values are used. On the search engine that we have for this approach, because we usually define a grammar, the mapping process, and we use an evolutionary algorithm to evolve a population of solutions. Here's no different. We'll have a population of possible solutions that are randomly generated. In this case, a population of possible UNets, UNet architectures, U-shaped networks. And we will apply a selection operator, crossover and mutation. We will evaluate those solutions and apply a replacement operator. So we keep evolving this population of possible solutions until we reach a stopping criteria, be it time, number of generations, a minimum quality we want to achieve. And because we are dealing with the design of neural networks, here we have to also include that to evaluate our solutions, we'll have a data set that will be used to train those networks and access the quality of that solution that, in this case, we opt to use the accuracy of the network. So now moving on to our proposed approach. This is part of the grammar we propose to design U-shaped networks. Here, the full grammar wouldn't fit, but in general, a UNet is defined as other feed-forward networks, a list of layers that can be for instance, a convolution, pooling layer, dropouts, and each of these layers have their own parameters like number of filters, kernel size, type of padding, be it and dropout has also their own parameters, and the pooling layer the same way. You have the kernel size for the pool layer, and here we define it the way that we define this grammar that we'll be showing in a minute is that we opt to just design the left part of the UNet, in this case the U-shaped the U network, and by doing that, our grammar is able to select the layers that will be applied on the learning part of the network that will learn the features, as I mentioned before, having flags where the bridges can occur. And after we define the left part, all the nodes that will grow in this part, that is the result of the grammar expansion. We add, the method will add the nodes to the right side that are related to the nodes of the left side. This happens because as we were studying the UNet and the architecture, we noticed that it has this symmetric philosophy where for each decreasing layer that would decrease the dimension of the image, on the right side you have an operation that will increase the dimension of the image. So when you input an image of, let's say, 256 to 256, the input can have similar values for the output. So here we defined our grammar to design the nodes that would be on the left. Then we added the nodes that are related to the left side on the right. And as a final step, as we added those layers, we make the connections between them also related to the values. So doing this way, we ensure that all the solutions we generate for the evolutionary algorithm are valid networks, and we avoid having problems with stagnation because we don't have valid solutions, or another costs involved in repairing the solution. We opt to have rather, let's say, restricted architectures, but all valid, instead of trying to repair a solution that adds to the cost. On the evaluation, so as we are dealing with segmentation problems, we propose the use of 4 image segment similarity metrics. Here, the Jacquard index, the DICE index, sensitivity, and specificity. And we added all them together in a weighted mean function where we can define different weights for each of the metrics. So we can give more importance to some of the metrics depending on the data set. Depending on the data set, some of these metrics will have more impact when measuring the quality of the segmentation. We also propose little modifications to the genetic operators that will perform try to increase the diversity in the population. And the crossover, for example, it does similarly to any other crossover for other problems where you have a random cut in the solution and you mix those parts from the parent solutions, you have a new solution. As we have all solutions with an important part is that here this cut is made only between the different lists for each different rule, and not like, let's say, in the breaking the values within a list. So by doing that, we ensure that we can generate new solutions that are still valid. And if there are, for example, cases where a solution has fewer values than needed, it will add those values randomly as in the generation. And if you have more values than needed to perform the mapping, the remaining values are just ignored. The same way for the mutation. Depending on how you structure your grammar, you can group all the rules that lead to non-terminals to be more on the left side of the encoding, the solution. and the rules that are related to terminal values more on the right side of the solution. So this way you can pick a random value. It doesn't matter if from which list you choose, and change for another valid value just by looking and by looking on the bounds for each of these lists. For example, if you for the operator, we have 4 possible values that are for that grammar I showed before, the plus, the minus, the division, and multiplication signs. So we can have from 0 to 3 here. So we can pick any value from this list and change to one of those values between 0 and 3. And the solution will still be valid. And again, if you need more values, those are randomly generated. And if you have remaining values, we just ignore. For the experiments, we tested our approach using 2 different datasets. The first one is the BSDS500. That is a dataset containing 500 images of size 256 to 56. And by definition, this dataset is divided in 200 images for training, 100 for validation, and 200 for test. We normalized the values to be between 0 and 1, and in this case, no dot augmentation was used. And the second data set is the ISBI12 that contains 60 images, 512 by 512. In this case, we applied dot augmentation, so we divided this data set into 300 images for training, 30 for validation, and 30 for test. The dot augmentation is applied only on the training portion of the dataset. The parameters for the evolutionary algorithm. We evolved a population of 20 solutions, evolved for a number of 25 generations. Here we applied a crossover with 60% chance of happening and mutation with 40%, and we opt to apply either the crossover or the mutation, not both at the same time. Because during preliminary experiments, we noticed that applying just one of them at a random chance was producing better results than having the chance of applying both of them. The tournament size, we use a tournament size with size 3. We maintain 10% of the population as elites. The models were trained during the evolution for 10 epochs with a time limit of 60 minutes. What happens first? The training is over or the time is reached. And the best designed network at the end of the evolution is extracted and retrained for 500 epochs to then be compared to the original unit. Some of the results we have here at the table for both datasets, the BSDS and ISBI12. We have the values for each of the metrics individually, and here on the right column we have the weighted average. Here we have that our best evolved network, I forgot to mention, but our evolution was run 5 times, 5 individual runs. So we generated 5 different networks at the end, and here we are showing the best one among those 5 and the mean result of those 5. And for these numerical values, our best evolved network was able to reach slightly better results than the original unit on the weighted average for both datasets. A side note, the weights we used for the metrics were 0.4 for dice and sensitivity and 0.1 for Jakarta specificity, because again, during preliminary experiments, those were the metrics that showed to be more important to evaluate the segmentation for these 2 datasets. Another analysis we made was by analyzing the evolution of our best evolved network on both the accuracy curve for training and validation and the loss curve also on training and validation. And here is the performance of our best evolved network, that both during the accuracy and the loss values seem to be very close to each other, which it makes sense. But when we, and this experiment was for the BSDS dataset, and when we compare to the same scenario for the UNet, we can see that for the accuracy during the training, the UNet was able to achieve very, very high values for the accuracy, but on the validation set, it didn't express the same performance, the same good results. Also, on the loss curve, we can see that, again, for the training, it was able to maintain a very low value, which is good, but on the validation, the curve didn't follow the same behavior. So we can conclude that our evolved network was a much more reliable solution compared to the UNet. And just to finish, this is some examples of the data set from the BSDS, the original image, the original segmentation. Here at the top, we have the segmentation produced by our best evolved network and compared to the segmentation produced by the UNet. Just by a visual analysis, we can see that it seems our evolved network was able to produce images with more richer in details compared to more clear lines for the UNet, but with less details, so to speak. So some of the conclusions we have from this work is that the proposed grammar was able to produce a variety of U-shaped networks, that the best generated network outperformed the original UNet. The output images are richer in details compared to the UNet, and evolving a population of architectures is very time consuming. And some of the next steps I can list here is to try to add more flexibility to the grammar. As I mentioned, we kind of restricted the power of representation of our grammar in order to ensure we have valid solutions, and improve the search engine and allowing the design of diverse types of networks, and searching for more efficient ways to evaluate the network so we don't have to keep training all these solutions to access their quality. The acknowledgements, and I now am able to answer some of your questions.
Okay, thank you, Ricardo.
I can hear you.
Okay, so we have time for some questions. Victor, please go ahead.
Hi, Ricardo. Thank you for the presentation. Let me consider choose some objective optimization.
We have too much noise. We can't hear you because we have too much noise.
Okay, sorry. Can you hear me now?
A little bit better.
Yeah.
Okay. Have you considered to use some multi-objective optimization algorithm instead of using this combination of different metrics in your fitness function?
I think changing the approach to consider multi-objective algorithms is not that difficult because you would be adding more different point of view when evaluating your network. Because, for example, if here we are just analyzing the accuracy of the networks as a way to express the quality, but I could be using both the accuracy, the loss, combining those, or maybe adding also a novelty factor to ensure our search was more towards trying to find different architectures from the original design. So I think it is feasible. I don't know if I answer your question correctly.
Thanks.
Okay, thank you for your answer. We have time for one more question. So we have one in the chat. Nuno, please, if you don't mind, turn the microphone and ask the question.
Should I read the question then?
I can read it if you want. So Nuno Rodrigues from the chat asks, did you think about evaluating the models in larger, more common data sets such as COCO and Pascal VOC?
It is difficult to plan experiments on more larger data sets because by running these experiments on rather small data sets like the ones I showed during the presentation took me already a long time if you don't have a GPU to help you. So I think it is possible to run the approach on different data sets. We did run this approach on artificial data sets in a previous stage of the research. Now we try to run it on real world data sets. And I believe it would be possible to run on larger data sets and common data sets to try to see if we can also generate good solutions. But right now, the main issue regarding the approach is really the time that you need to train all the population. And that's why we chose to use a very small population and very low number for the generations.